for
oh. It didn't move. I like that. So number 4 says if you randomly generate numbers from
0 to 9.
0 to 9,
Yeah.
can the methods of this section be used? So if you randomly generate numbers from 0 to 9, what's the probability I get a 0? What's probably get a 1?
1 out of 10.
Yeah, 1 out of 10. If it's randomly done, they should all have the same probability of showing up. And so I get a 1 out of 10 chance. What kind of distribution would that be if I graphed it then?
Uniform.
Uniform. Rectangular, I know what you mean. So uniform. So could I use the z-score chart? No, because the z-score chart only works for normal distributions. So that's the real key point here. That is a valid probability distribution, but it's not a normal probability distribution. So I can't use the methods from this section.
So it's no, but then you can still.
You can still do it.
Yeah.
You could use the idea of a uniform. So to get less than a 5, all you have to do is 0, 1, 2, 3, 4. So that's 5 out of 10. That's not even uniform. You can think about it. That's actually from chapter 4. Right? Cool. 5 out of 10 numbers. They're all equally likely. So it's 5 out of 10 probability. Cool.
And then I had a question from 6.4, but I don't know if we're going over it today because it's not something we had talked about.
Oh, what's that?
It's number 9. They're asking about the median and like comparing the median to the mean. Like the whole, I didn't understand it. Like,
So
honestly.
when they ask you, the example I gave you on that very colorful handout was finding a bunch of samples and then finding their sample means.
Right.
Right? So they have like that, blah, blah, blah. Now, I could get a sample and find other statistics about that sample. I could find the mean, I could find the median, I could find the standard deviation. Those would all be statistics because they're all from my sample. And then I can make a list of those. And then I can do the same thing that they're asking me. I can average those out and see if they're the same as the whole population. So it's the same idea. It's just instead of getting a mean there, I would get the median. And the funny thing about the median for a sample of 2, if I take 2 numbers, the mean is the number that's right in the middle of them, and so is the median. So the median and the mean will be the same. Cool. But the real question there is the average median the same as the real median of the population, where I got these numbers from? That's the real question, right? Shoot. All right. So on that thing, we did the X bars. We got all the means. If you take the mean of the means, it's the same as the mean was in the first place. So if I have the numbers 1, 2, 3, 4, and a hat, the mean is 2.5. If I do 2 at a time and take each mean and average those, it's still 2.5. So far, so good? Now the median, it doesn't really necessarily always work. It depends on how big the list is. And it depends on several other things. Here, the mean and the median are the same because that's a very simple 1, 2, 3, 4, 2.5 is right in the middle. But all I have to do is do this, and suddenly the mean and the median are not the same. You guys with me? Yeah.
How's the median change?
I said the mean and the median are not the same. I didn't say that the median changed. The mean changes. So now the mean and the median are no longer the same. The mean here, the median would still be 2.5, but the mean would be 11/4. So whatever that is. 2.75. You guys kind of with me here a little bit? So all you have to do is, if they say standard deviation, make a list of standard deviations. Well, how do you do that? Put these in your L1 and they would do 1 bar stats and get the little s. Now for this one, that'd be easy. What's the standard deviation for sample 1, 1? What's the standard deviation for 1, 1? 0. It doesn't go anywhere. What's the standard deviation for 1, 2? I don't know. Put them in the list 1. Do 1 bar stats, get the standard deviation, put it there. 1, 3. 1 bar stats, get the standard deviation, put it there. Cool. Okay, maybe. So we got several examples in that section. It just takes you sitting down and doing the work. And the work is actually relatively easy because you're only working with samples of 2. And you can put them in your calculator, do 1 bar stats if you like. Yep.
When you say putting in a 1 bar stats, is that gonna be like one's gonna go into list 1, 2's gonna go into list 2?
Mm-mm. This is one variable, so it's a one list.
Oh, so it's 1, 1.
Yeah.
Okay.
Yeah. So I would put in list 1, 1, 1, and then I could go to 1 bar stats. It'll give you the mean, it'll give you the median, it'll give me the standard deviation. So I could do all 3 at once, by the way. Make 3 different tables. Cool. Yeah.
So when it says like a population consisting of 2, 3, and 10, you just do 2 and 3, 2 and 10, 3 and 10. You just
Yeah, 2 and 2, 2 and 3, 2 and 10. 3 and 2, 3 and 3, 3 and 10. You can be very systematic about it.
You can have them be.
Oh yeah, you can set it up just like it did this one. This is 1 and 1, 1 and 2, 1 and 3, 1 and 4. 2 and 1, 2 and 2, 2 and 3, 2 and 4, blah, 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 blah. So you want to make sure you capture everything that could possibly happen. So in 2, 3, 10, you gotta go 2 first and a 3 second, or you could go 3 first and a 2 second. So those are 2 different situations.
So it's assumed with replacement then. So you pick 3.
Definitely.
3.
With let's see what
Because
it
it
says.
says from the population consisting of 2, 3, and 10, where the values are numbers of people in households.
Yep, 2, 3, and 10. And actually here they say without replacement, so they make it even a little bit easier, which is funny to me. But oh well.
What did they say without?
And they've actually, the beautiful thing for the problems you have to do in 6.4, I really want you guys to realize this, they've already made the table for you on page 271. They've already done your samples. You just have to now find the median, the standard deviation, right, and the, I can't remember which one otherwise I gave you, variance maybe, right? You just have to find those 3 things.
But since it's without replacement, we don't use 10.
Yeah, you don't have to do 2, 2, yeah.
Okay.
Yeah. They should, but I guess they did that just to make the list shorter. Okay. All right, yeah.
Can you do number 2 from 6.3?
Oh, all right, what's always the total area under a normal curve?
1.
1, okay, so part A is easy. The total area under the curve is an area of 1. Part B says, what's the value of the median? And here they tell me that the standard deviation is 15, the mean is 100. And this is true, by the way, so if you know your IQ, you can figure out relative to where you are. Figure out your Z-score, and figure out where you fall. Right? Forrest Gump, down to 70. There's 2 standard deviations down. Little Forrest Gump. So part B says, what is the value of the median? Remember something nifty about the ultra-symmetric normal distribution? The mean is right in the middle. The median is the number that's in the middle, so that's going to be right in the middle, so it's also 100. And in fact, part C, the mode, where's the tallest part of it? That would be the mode. Wouldn't it? The one that occurs the most is the tallest part. And of course, that's
The mean.
right in the middle, so 100 again. So they're really just trying to hammer home the idea that for a normal curve, the mean is the median, is the mode. If it's truly perfectly normal, that's true. If it's approximately normal, these should be close, at least. Okay. So that's all that problem is really about. It sounds like you have to calculate something, but when it's one of those early 4 or 5 problems, there should be no calculation. It should be conceptual. That's all that is. Yeah.
Can you do 24 and
6.3?
Yeah.
Oh, cool. So here they tell you that men's heights, the mean is 69, standard deviation is 2.8. Women, mean is 63.6. Okay, cool. So that's close to right. I think earlier I was using these 2. I mixed them up. So the men's 2.8 standard deviation, a little more spread out. Now here's what I was talking about earlier. I love this. Tall Clubs International. Why not? has minimum height requirements, that makes sense, right? Can be a tall club. If the requirements are changed so that the tallest 4% of men are eligible, this is number 24. So if I'm the tall club, I want to take these people here, right? The tall ass people, and then leave the rest of us out. Whatever, that's fine. So the top 4%, of course, has to be up here. So don't do this. That's really evil to yourself. I'm evil to you. Don't you be evil to you. That sucks. Don't put areas down there. You only put z-scores down here. 4% is an area. It's going to go up here. So this is the kind of problem that I did not put on this quiz that I actually had on there originally, and I said, what the hell, I take it off. Where they give you the percentage. You then have to work back to get the z-score, and then eventually get that back to the x-score, right? And last time we did this beautiful little formula here. You start with this, and you do some algebra magic, and you get down to there, right? And this was an awesome formula because it's the definition of z-score. The z-score is a number of standard deviations away from the mean to a data point. That question that will be on every test. There's the answer on your formula sheet. That's awesome. Still, somebody's going to get it wrong. I know. But I just accept it anymore. So if I can find this z-score, I know the mean and the standard deviation. I can then figure out what the height is that goes along with that. How tall does somebody have to be like the boundary for the top 4%? So then I'd say anybody taller than that, we'll take it. Right? Check your shoes. Make sure you don't have something in there padding your way in. I don't know why you want to be in that club at all. So what is the z-score? How do I find that z-score? Do I look up 0.04? You could. So there's a shortcut. You can look up 0.04 as long as you realize it's supposed to be positive. When you look up 0.04, you get the negative. If you don't like the shortcut, what should I look up?
Subtract the 0.04 with the...
Yeah, what's the area below here? If that's 4% up there, this must be 96%. So if you look up 0.96, the closest I can get to 0.96, if you want one of these, by the way, you can grab one and keep it. And you just bring it with you always.
It's 1.75.
1.75.
Yeah, good. So the closest I can get is 9599. That's damn close to 96. You guys see that? 9599. That's 1.75, like you said. Cool. So z-score is 1.75. So they're 1 3/4 steps above the mean. So now if I use that formula, I'll figure out what height do I end up at if I do that. If I start at the mean and I go that many steps, standard deviations, where do I end up?
The height.
The right height. Good. So then I'll just plug that in the calculator and figure out what in the world that is.
0.9 inches.
7, 4.9, 73.9.
Yeah.
Yeah? Okay, cool. So if you're 73.9 inches tall or higher, they will let you in.
Well, that would actually lower it, wouldn't it?
What's that?
Yes. That would lower the height requirement.
From number 21.
Yep. So they decided to let more people in. I guess they didn't have very large numbers of people. So they said, okay, we'll let some more people in. Yeah.
That extra 1/10 of inch.
Yeah. You never know. Now they're going to come knocking down the door. And then part B, I'll let you guys do. That's women. So just do the same thing we did here, using the mean and standard deviation for women. Cool. All right. Anything else? Okay. You guys gotta spook me out. Your dog's just. All right. I think several of you are working on your 100-yard stare and using it on me. I'm your test subject, and it's working. So last time we talked about central limit theorem.
Yes.
So let's do a quick problem that illustrates that idea. Then I wanna finish out chapter 6 and hopefully do one section out of chapter 7. That's ambitious, but that's way. So, we know the mean grade was 70.1, standard deviation of 9.52. So this is sort of like that question on the quiz. On the quiz, I had to say, assuming this is normally distributed. If I didn't say that, what could you have technically said and been completely right?
No answer.
Yeah, can't do it, Jeff. That was quick. Can't do it, Jeff. So the book is guilty of this. For some reason, Triola sometimes does not put that they're normal. You just have to assume they're normal to do the problem. So if you want to put down there, well, it's not. It doesn't say it's normal, but I'll do it anyway. You probably should do it. If you want to, you can say, I don't know, Jeff, it doesn't say it's normal. Fine, but still do the problem. Right? On a quiz or a test, I'm not going to give you a trick question where you're not supposed to do it. That would be a little evil, because then some people would see it and other people would waste time. That's a little mean. I'm not going to do that. So you always assume that I want you to do it no matter what. But in reality, if I just started asking questions about probability now, we couldn't do it. But if we say 48 grades, randomly take 48 grades, what's the probability higher than a 73? Why can I all of a sudden do this problem? What tells you, according to the central limit theorem, right? What's the probability that's higher than a 73? The mean, the sample mean.
Oh, right.
Yeah, that's.
Because it's
Sorry.
lower than 30, it's normal enough.
Good. Why do I know that this is normal enough exactly?
More
Yeah, I took a sample higher than 30. That I know my sampling distribution, my distribution of mean grades is definitely approximately normal. I like that. Definitely approximately. Because of the fact that it took more than 30, a sample of more than 30. That's the heart of the central limit theorem is that. And the other things it talks about is the mean stays the same, but the standard deviation does what? What happens to my standard? What's the new standard deviation?
Smaller.
Smaller. This is true. Numerical. That's true too. Positive. That's right. Can we be a little more specific? The new standard deviation.
Is the old standard deviation over the square root of the number, which in this case would be 48.
So it does get smaller. It gets smaller very specifically by this. So the bigger my sample, the smaller my standard deviation should get, which goes right along with what we knew on day one. The bigger the sample we take, the more sure about what we are about what we see. Okay. So, I mean, on the surface of this, this sounds just like a problem we had on the quiz. I'm asking for the probabilities higher than 73. I gave you the mean and the standard deviation. You can draw the picture, make a z-score. The problem is, this is not normal, and to make it normal, I have to take a sample, and the minute I take a sample and I ask about the means, I have to do this first. And that's really all that changes. That's really nice. So what is the new standard deviation? The old one was 9.52. What do I divide by square root of what? 48, because that's my sample size.
I got 1.37. Yeah.
1 point, you can do it, Jeff. 1.37.
Oh, 4.
4. All right, so that sounds good. Everybody else got that?
Don't you only want us to go to 2 decimal points because then that is far we can see it.
That's not a z-score.
Right.
And now, that's one extra step compared to 6.2 and 6.3. That's one extra step. And now everything else is the same after that adjustment. I can draw the picture the same, there's the mean in the middle, 70.1. Here's my score, I want to know higher than that. I make a z-score the same way. The official formula is this. It's the same stupid formula. My score I'm interested in minus the mean divided by the standard deviation. You just have to use the right standard deviation. So this z-score, how do I set up this formula? 73, that's my score. Minus 70.1, that's the mean over the new standard deviation. Cool. So it's like 2.08, I don't know.
2.11.
Yeah. Okay. I can do that. So what's the z-score of the mean?
0.
0. And the z-score for 73, we just calculated it to be 2.11. And I highly suggest you do that for yourself so that you know where to put things when you look them up. So when you look up 2.11, it goes off to 70. I know we've only got one data point up here, but get used to that. What do you get when you look up 2.11?
0.9826.
Yeah. So does everybody agree with that? You gonna take his word for it? You gonna let him do your work for you? I wouldn't. He's a smart kid, actually. He's probably right, but we better double check. All right, if you do double check, I like that. So 2.11, 0.9826. So then what's our answer then? 1 minus that. Cool. I like it. And some of you guys might know the shortcut. If you look up, and here you can still use the shortcut. If you look up negative 211, you'll actually get 0.0174 directly. Be really careful. If you don't quite understand it, don't use it. Right? Because you're going to use it in the wrong way at the wrong time. That's going to suck. Okay, how are we doing? Is that? So that's 6.5 is the same as 6.3. It's just that your first step is to know, do I do this? And then you do it when you're supposed to do it. So what is it that tells me I've got to do this?
More than 30.
Yeah. When I take a sample and I ask a question about the sample mean.
Oh, so for that one, then there will be problems where we don't do it, or we say we can't do it because it doesn't meet the criteria.
Yeah, I mean, if they might give you one that says, tell me if you can do this or not,
Oh, I see.
and tell me why. Right? So if they said, if they had this set up and they said take a sample of 16, you say, well, you never said it's normal and your sample's too small, so I can't do the problem.
If they said it's normal and then they give you a sample.
Good, I love it. If it starts off normal, how large of a sample do you need to take to make it normal? 1. It's already normal, right? So it doesn't need 30. 30 is just if I don't have a clue about it. This could be normal, but what do we have to assume? It ain't. So I need a sample of more than 30. If they tell me it's normal, I don't need a sample of more than 30. In 6.3, they told me it was normal, and I was picking one thing at a time. I could do the probabilities, no problem. Yeah.
Okay, so the 0.0174 that's 1.74%.
Good.
chance
It's an almost 2% chance that
that if picking
a
40
sample of 48 grades would have an average higher than 73. And if you think about it, that makes sense. The actual average was 70.1. If I take a sample of 48 grades, they should have an average close to that. So it should be very small probability that the average would be above 73. So it all makes sense. It should be close to this, not way out here. Okay. All right. Okay. So that's 6.5. So now we're going to get into 6.6.
Forgot there was a 6.
Okay. So really the whole point there is if you understand 6.3, you should definitely have very little trouble with 6.5. It's just one little concept and one little adjustment on your standard deviation. If you're having a lot of trouble with 6.3, please come see me. guy. It's a hugely important section. This section introduces something we're going to use later, and it's also just another example of a tweak we can make to a normal distribution. So I love the title of this section, and actually this would be the normal approximation to the binomial distribution. Something I'll call the NAB for short. Right. Anything that takes the whole board to write sounds intense. So here's the idea with this. And we've seen this before. And on that handout that I gave you guys, let's see if I have a copy of it right here somewhere. With the flipping a coin. I think I gave all mine out. And it had, looked very, well, just to pretend.
You mean the paper one?
Yeah.
With the, one through 4?
No. The handout I gave back in chapter 5, that had to do with flipping a coin. And I flipped it 14 times, so the probability was 0.5, so the mean was 7. So forth, yeah. So we mentioned that looked very normal. It looks normal. But we are at the point now, we're way past chapter 2, where we first started talking about the things look normal. I want something more substantial. I don't want to have to say, it looks kind of like a bell. I want some freaking numbers. If it passes this test, it is normal. If it doesn't, it's not. I like that. Give me that. So this looks normal. Now the problem is, what's the problem between this curve and these rectangles? I mean, I can draw a curve over the rectangles. Ooh. Mathematically, there's a huge problem with that.
There's the height and the height.
All right, I like that. One square, one's curve. What is this? What are the sides of this bar right here?
The distance.
What are the sides of that bar?
You subtract from the.
This will be 6.5?
7.5.
7.5. You with me? All right, so technically, this is 1, 2, 3, right? 0, 1, 2, 3. Is that continuous?
No.
No, there's huge jumps. I put bars in it. Now look, the bars make it look continuous, doesn't it? Now the bars flow, right? So it makes it look like this belongs more on top of it. But what that really means is, in order for this to work, in order for us to use z-scores to calculate probabilities for binomial, that's what we really want to do here, isn't it? Use z-scores for binomial problems, right? That's what we want to be able to do. We have to somehow use this adjustment here so that we can pretend like it's continuous. Whenever I say that, people kind of tune me out. Maybe that I'm pretending in math and it's imaginary and all this kind of. No, we have to kind of adjust it to make it fit more a continuous curve. So let me first tell you, why would I even want to do this kind of weird crap? Because if I had a sample of 8,000, and I want to know, let's say 8,000 people, and I want to know the probability that at least 3,998 are left-handed. Now, if you had to do the formula, how many formulas would you have to do?
Millions.
Way too many. Right? Around 4,000 formulas. I don't care if you make it the opposite, at least 3,998. The opposite of that is 3,997 or less. So either way you go, you're screwed. This is not an at least one. At least one is beautiful because its opposite is small. There's only one thing in it. Here, they both have about 4,000 things in it. So you'd have to do 4,000 of these formulas here to actually figure out what the probability is. All right, well that sucks. I think you all agree with me on that. Yes, sir.
I thought the choosing was so you didn't have to do all those.
No. Nope. I mean, this would be, I could do at least 3,009. So I can do 8,000, choose 3,998, blah, blah, blah. Or 8,000, choose 3,999.
Oh, that would show you the actual percentage of getting that.
Exactly that. So if I want at least or at most, I have to add several of them together. Yes, cool. If I do a single formula, that's just exactly 3,998. That does not answer this question. Okay, all right, maybe. You guys look excited. So that's the motivation behind this. So here's the actual test to know, because I'd much rather, I can get the mean. And remember the probability of left-handed was 0.11? So what's the mean in this case? How do I get the mean in this case? N times P, 8,000 times 0.11. So 880, I believe. Cool.
Wait, how'd you get .11?
Oh, remember that was the probability of being left-handed was 11%.
Oh.
We probably did earlier. That's not something I calculated somehow out of nowhere.
Okay.
What's the standard deviation? How do I get the standard deviation?
Let's go to the 1B.
All right, so somebody help me out. That would be 8,000 times 0.11 times, what's Q? 0.89. So somebody help me out. I'm not going to try to do that in my head. At least not all the way.
8.85.
Thank you. You saved me. 8.8.
49.
49?
498.
4.8, so it's 5. That's good. I like it. Okay. So we've done this before. This is nothing new. This is back in section 5.5.
Oh, sorry, I did it wrong.
Oh,
That's
shoot.
not what I got.
27.9857.
That sounds better. I knew it was 27.986.
9857.
Okay. So we've calculated the mean and the standard deviation. That should make us feel like we could do z-scores and we can use them like we do now in chapter 6. Instead of doing all this to get the probability, I should maybe in some cases be able to use these to make z-scores to get that. That would be easy then. I could draw this picture, put 880 in the middle, probably at least 3,998, get that area.
Wait. Wouldn't you put 800?
The mean is 880.
8,000.
The mean is 880.
8,000 total.
Yeah, total is 8,000. So the mean is 880. The average number of left-handers out of any group of 8,000 is 880.
Right.
And the Q? The Q.
The Q is 0.89. Yeah, Q is 0.89. If P is 0.11, Q's got to be 0.89. Okay, cool. All right. So that's the motivation. I don't want to do this work. Right? And I don't blame you in this case. And it looks like I should be able to use z-scores. So when is it normal enough? That's really the question again. So we saw one with central limit theorem. When I have a continuous set of data, like men's height, or grades on a quiz, or something. When do I know it's normally distributed? When I take a sample of more than 30.
Right.
Here, when I have discrete data, when I have 0 people, 1 people, 2 people, how do I know it's normally distributed enough? Here's how you know. I think I mentioned this before. This looks pretty normal, that picture from the handout from before, because it's got room to go up and down. It's got room to do that, because the mean is right here in the middle. What if the mean was right here? This would look like this. Does it have any chance to be normal? No. What if the mean was, now of course with a binomial there's a maximum number, right? If I have 14 flips of the coin, the most it could be 14. So what if the mean was up here? It'd have the same problem, wouldn't it? There's no way it can go up and down because there's no room to do that. So it's got to be right in the middle. So the way that we do that is the mean itself, the NP, has got to be greater than 5. If it's greater than 5, that gets it room to go up and room to come back down. Now you're going to love the other side. How do I take care of the other side?
Less than 5.
No. It can't be greater or less, because then that would be everything, right? So the mean NP has got to be greater than 5, and the cool thing is the average failure has got to be greater than 5 also. So NQ must be greater than 5. That is your check for a binomial to see if it's normal enough. Yeah.
And so that's if it's normal enough to do.
To use z-scores and look them up and get the areas like we did in section 6.3.
Oh, not normal enough to take a sample to make it normal.
No, no. So let me make a little bit better problem, because that greater than 3,998 left-hander is going to be 0. I can't get more than that. So let me make a little tiny problem here. If I had 80 people, and the probability they're going to vote for Romney is 48% chance, and the probability they're not going to vote for Romney then would be 52. First thing you want to do is check to see if it's normal. Bless you. So, and the nice thing, I am very nice with these problems nowadays. I didn't used to be. So I've kind of done the reverse. Normally you get harder as you get older. I ask you, verify this is normal. Enough. Check. I even get even. I shouldn't even do this. Check NP, NQ. So what is NP in this case?
88.4. You multiply.
Yeah, multiply 80 times 0.48.
38.4.
38.4?
Yeah.
Okay, that sounds right. And that is greater than 5. Good. So far so good. NQ,
41.6.
41.6. And notice that these add up to be 80. You guys see that? So if the average number of successes is 38.4, the average number of failures must be the rest, 41.6. If you don't see that, who cares? You can still do this little equation. So that's greater than 5. And what does that tell me, those two things? It's normal enough to use Z-scores.
So 41.6 people won't vote for him.
Say again?
41.6 people won't vote for him.
Out of a group of 80. On average. Don't worry about that 0.6 person. Freaking everybody out in the polling station. So now I can draw this picture. I know it's normal enough. I can go ahead and draw a nice normal distribution. The mean was, and the nice thing is I've just already figured out the mean. The mean is 38.4. What's the standard deviation going to be?
0. It's the middle, 0.
No. Not the z-score. The standard deviation. So square root of NPQ. It's like 4.465? 69?
Yeah, that's right. 4.4685.
I like it, cool. Now I can ask you a question like, what's the probability that less than, what, Jeff? I don't know, less than 30 people will vote for it out of a group of 80? So here's where we have to be careful. Here's where the trick comes in that I talked about earlier about using the fact that these are really rectangles here. So when I draw this curve, it's normal enough so I can draw that curve, but here's where you got to be careful. Put on there 30. What is really around that 30 is that block, right? If I want to be, now that block represents 30. Are you with me? So 30 is actually from
29.5.
29.5 up to
30.5.
30.5. So if I want less than 30, I'm going to shade down, right? Do I want to include 30 or not?
Less than 30.
I don't want to include 30. So do I start here and shade down, or do I start here and shade down? Do I start on the back wall here or on the front? Yeah, I start there and shade down. I do not want to include 30. In order for me to use a continuous curve for these blocks, I have to pretend like there's no 30. There's just 29.5 to 30.5. Then are there any gaps then? Are there any gaps then? If I just say 0, 1, 2, 3, 4, there's these huge gaps. But if I say, no, 1 is really 0.5 to 1.5, and 2 is 1.5 to 2.5. See, now there's no gaps. And that's how we made the histogram, so they'd have no gaps. So in order for me to pretend that this is a normal distribution, and this tells me I should be able to do it. And in fact, another way to look at it, in order for this approximation to be better, I have to use one side or the other. I have to adjust it a little bit. So that's the one switch. Back in the central limit theorem, the one tweak was the standard deviation becomes divided by square root of n, right? For this problem, for a NAB problem, I've got to do what's called the continuity correction. That's an awesome name. This is the continuity correction. I'm correcting for the fact that it's not continuous. Yeah.
I forgot, why are they rectangular? Why aren't we just using the curve?
Because the problem itself is not a curve, right? If I have, where's my original problem? Oh, here. So I had 80 people voting for Romney, blah, blah, blah. 80 people. So is it possible to have 7.39 of them vote for Romney? No. So it's not continuous. So they are blocks in reality.
Because they're full people.
Because they're full people. So in order to pretend to be continuous, I have to fill the gap in somehow in between one person and two people. How do I fill it in? By putting a block around one and saying there's not really one people. There's half a person up to 1.5 people. That way, isn't it now continuous? Are there any gaps? No, it's continuous now. So trust me now. We're actually gonna take a look and see how good this does compared to what if you didn't make this continuity correction. How bad would it be? So what that does is this becomes, by the continuity correction,
Which is view protected.
I know you guys love this, but central limit theorem, one tweak. Change the standard deviation, everything else the same. NAB, one tweak. Change the number up or down by a half, everything else is the same. Okay. So this becomes then x less than what? 29.5, because in order to not include 30, I had to shade from this side. So I have to actually start at 29.5. If I would have said less than or equal to 30, I would have started up here. Then my correction would have been 30.5. So now, this is a question I think you asked last time, Mike. This is where the less than versus less than or equal to completely changes things. Because of the fact that I do have in reality 30, 31, 32. So now the areas do matter for each individual one, because now I have a whole block for an area, not just a line. Okay, hopeful. So to finish this problem out, I make a z-score out of this guy now. That's the number I use. Just like on essential limit theorem, I use the new standard deviation in my z-score formula. On a NAB problem, I used the new number, the adjusted, the continuity correction number to get a z-score. What goes here? 38.4. My data point minus the mean divided by
4.469.
good. The standard deviation we got, which was here, 4.4. Same old formula, same old idea. I look it up, I get the area. In this case, I'll be done because it's below, right?
Negative 1.99.
Negative 199? If you look up negative 199,
.0233.
cool.
And that's percent chance
So there's a 2% chance, just over 2% chance, that out of 80 randomly selected people, less than 30 of them will vote for Romney. Okay, cool. All right. Okay, maybe. So what I want to do real quick, and I'm just going to have to give up all my dreams for chapter 7. So, and don't leave too quickly because I have the practice test. I have to tell you which one is not going to be on the test because we're not going to do any chapter 7 yet. If I would have done the z-score without doing the continuity correction, what would this be? Somebody help me out. See, that's without using the continuity correction. If I would have made that mistake, what is the z-score now?
1.88. Negative 1.88.
Negative 188? Confirmation.
Yeah.
Other people like, I didn't do it, but that sounds okay. I like that. Just to move things along, Jeff. So negative 188, if you look that up, that would be, I lost it again. Negative 188.0301. Okay. So what you say, that's kind of that is actually a pretty big difference between just over 2% and just over 3%. Now for some of us, that's a big difference. 1% difference is actually kind of big. So which one is more right? We can actually do this problem. If we can do that, we can have the calculator do this for us. Which again comes back to, well, why are you making us do? Oh, just suck it up. So binomial CDF. Why am I going to use C instead of P? Because I want to go from 0 up to, I want to be a cumulative probability from 0 up to not quite 30, right? So I'm going to put in here NPX. I'm going to put in here, what was it, 80 people? 80 people, 48% chance, and X in this case, now be careful, if I want less than 30, I want to go from 0 up to 29. Why do I not have to put 29.5 or something in there? Because this is a binomial probability I'm using, not a normal. So I don't have to adjust that number at all. So let me do this with you. So if we go to second, just to remind you guys, vars. This, you have to scroll down to, for me, it's B, option B.
So X isn't 29.5?
Like I just said, here, what distribution am I using? Normal, and it's actually binomial. Here, what distribution am I using?
Binomial.
Binomial. Do I have to adjust anything? No, of course not. They match. It is a binomial. I am using a binomial. It is a binomial. I'm using a normal. Oh shit. I have to adjust it then. That's the whole idea. Here we did a normal distribution process for a binomial problem. I've got to adjust that. Here, I'm using the shortcut binomial process. I don't have to adjust anything. In fact, the calculator would freak out. It wants whole numbers in there.
It actually works.
Where do you get the binomial?
Oh, it does?
Yeah.
Alright.
Same number too.
Oh, okay, so it just takes it down. It assumes what you really mean.
Yeah.
I'm with you, okay?
10097.
So
0097.
0226.
How did you do it?
Make sure you have a C, binomial CDF, not PDF.
CDF, BDF.
Wait.
Ours is right next to clear. Yeah.
I got -1. Cause you did normal CDF. Oh, that's what happened.
All right, now which one is this closer to? Closer. Is it closer to our NAB, our approximation, or is it closer to if we made a mistake? Yes. So this is never going to be, not never, but it's almost never going to be this exact number. It says it in the name, NAB, normal approximation. But when I do this, it makes the approximation much better. So that's section 6.6. Oh, so here's a practice test.
We're getting over that on Monday, right?
Never again. Yeah.
When do you know we're gonna have to use that? Is it
No,
when
no.
we're not
That's what we want to see. Right? No,
Ah, look at number 7.
yeah, of course. It's there already.
It was originally on Monday. That's what it says on the slip.
So I am really nice with this. How do you know when to do this? I'm actually going to say, use the NAB to find the probability that.
Yeah.
I am still leaving it up to you to remember what the hell NAB means.
So which one are we doing now?
Did he say he was moving it fast by?
Let me check it.
The test is Monday or Wednesday?
Wednesday.
Yeah, that was.
And real quick, guys, number 8 is from chapter 7, so it's not going to be on the test. So just cross out number 8 for now.
Good, I don't mind. Which problems are we cross off?
Number 8 in chapter 7. Oh, thank you. Of course not. Beautiful. Make sure you have a front and a back on your practice test. My awesome printer. Oh, thanks. No, you don't have to. Oh, if you want to. Really, it's just taking the mean of these two. What's the mean of 1 and 2? What's the average? We got a 1 and I got a 2, it's 1 and a half. There you go, 1 and a half. The average of 1 and 3 is 2. So in the book though, when it's the standard deviation, I can't just look at it and tell what's the standard deviation of 1 and 2. So then you can put it in list 1 and do 1 bar stats to get standard deviation. But my suggestion was, if you have to do that for standard deviation, you might as well just do each one and then just do one table with a mean, one with a median, because it gives you all of that. So you might as well just do that to make it quick.
I was absent from
Oh.
I don't know if it's graded yet. Me too.
Yep. Emily, right?
Yes.
I was looking for my question. Hillary.
Hillary,
Thank you.
make corrections on that.
All right, thank you.
I was actually doing a few months like last day and I missed.
Oh, you missed the quiz thing?
Yeah, I was only doing, usually like take that like engineering class, right now,
No, but, that's the quick answer. But I can give you a copy of it so you see what was on it,
Okay.
if I find them.
Is there a way
Oh,
I
here
can
we
do,
go.
do a makeup?
No.
No.
What's gonna happen, you're not gonna have a 0.
My test grades?
Yeah, exactly. So
Okay.
your test just effectively is worth a little more.
Okay.
Yeah.
Thanks a lot.
Sure.
Since I'm too tired with that. I'm doing much work for exercise. YouTube, something like that.
Oh, yeah.
So that I'm late with my homework. I'm working with the homework. Because I have today I'll be able to work with this that you have given that until because I'll forgetting, so that I have to practice much
Oh, yeah.
more, so that I didn't have time to make the exercises, the homework. I go
So-
to tutoring and I go to there and everywhere, so that I have to. So will that make me
So wait, when you go to tutoring, then what do you work on?
with tests and quizzes and
Oh,
something like that.
and handouts.
Sometimes, yeah, handouts.
I
Sometimes
see.
with homework,
Okay.
Because they don't give you much time. They don't give you. They'll give you half an hour like that,
So the homework is not worth enough to really hurt you a lot, but it could possibly.
Yeah, but no. At last, I will bring it at last.